Okay, next in our little electric fields journey, we're going to once again think back to gravity a little bit. And one of the things that you guys took when you guys did gravity is when you have a mass of some kind, and of course you have a smaller mass, and you guys did stuff when the mass would go around and orbit and stuff like that, and of course that's where your forces kick in, and we've done that as well. But you also did stuff where the mass would either go closer or farther away, and of course when it was going farther away or closer, this is where you guys instead used energy. And the same idea applies to subatomics. There's no difference. So for what you guys did in gravity, you guys had gravitational potential energy was equal to gmm over r. And you could calculate the potential energy at any location, didn't make any difference. And of course, then the change in potential energy was equal to the change in kinetic energy, was equal to the work done. It was this type of thing that you guys did with gravity. Well, the exact same thing is used when you calculate electric potential energy. And the same way we switched out quantities for the G's and the M's, and that kind of stuff, we guys did forces and fields. Same thing here. Instead of the G, we have a K. Instead of M's, we've got Q's and over radius. And this is how we can calculate electric potential energy between charges. And again, it does all of the exact same thing. And that's why, again, if you can do the gravitational stuff, it makes this so much easier because it's all the same ideas over and over and over again. So, for example, if we had a large charge over here, and you had a smaller little tiny q over here, that little q up there, it has potential energy. And maybe this is a negative charge, so it would be attracted. Well, as it goes down, it will have a change in potential energy, which will be equal to its change in kinetic energy, which can be used to find how fast it goes, etc., etc., etc. And this is the exact same type of thing that you guys did with the gravity calculations. So once again, it's all the same ideas. Okay, so we've got electric potential energy is equal to kQq over r. Now, when you guys did your parallel plate stuff, and you guys had parallel plates, you guys also calculated electrical potential energy for parallel plates, and you had an expression called QV. And this is how you got one of the ways you guys calculate electric potential energy when the charges were inside of a set of parallel plates. And what you guys also did is we took out the Q over here and we were left with the V, and that was electric potential. Well, the exact same thing can be done with this expression, where if you remove the Q, you will be left with electric potential. So electric potential for this one would be the voltage again, is kQ over R. Okay, so it's the exact same idea that you had in the parallel plates thing. There's no difference. Okay, so let's sort of lay this out a little bit. Okay, so suppose you have a large charge of some kind. Okay, and here's a point in space. There's nothing there, it's just an empty point in space. So what you could do with this is you could find, first of all, if we go back to what you guys did a while ago, you guys could find the electric field, which was kQ over r squared. You could find the electric field there. You could also calculate the electric potential, which is kQ over r. And I know they look almost identical to each other. Now you can't find force, you can't find potential energy because there's nothing there. But once you actually put a charge there, so let's introduce a charge. If you actually put a charge there, then the electric field can be used to calculate the electric force, or just QE is sort of the shortcut. This electric potential now supplies that charge with potential energy, which would be kQq over r, okay, or just QV is the short one. So it's the idea of, any charge gives off a field, any charge can supply electric potential, but then when you actually put something there, The field can then result in forces. The electric potential can then result in electric potential energy. And we have got these four equations. Two of them are always sort of paired together. And I know they all look very, very, very similar to each other. And that's why it's really important, if you haven't been already, making a formula sheet for yourself, a formula list for yourself. Can come in really, really handy. And of course, the more you do this, the more familiar you will become at actually using them. Okay, and this is the basic idea behind how this stuff sort of works. But once again, just like we did with gravity, when we're talking about using fields and forces like this, typically, this is for things like things going in orbits, like charges orbiting and that type of stuff. And this type of stuff is when we change the radius, just like with gravity stuff. So these are the typical common applications. So it doesn't mean you can't use the forces and stuff that when radiuses change, but it's a lot easier typically to use energies for that type of thing. So when orbiting, there's your forces, getting closer or farther away, changing the radius. That's where you typically want to use energies. It's very, very similar to what you guys did with gravity stuff. So let's practice with this a little bit. You've had quite a bit of practice with the whole electric fields and forces and that type of stuff. So now we'll practice this aspect as well and look at how we can apply this when charges change the radii or distances between things. Now there is one key big thing got to be careful of. These guys here, the fields, and those guys were vectors, and as a result, we used arrows for those ones. These guys right here, those are scalar quantities, but you have to make sure they can be positive or negative. And it seems kind of weird to put a negative on a scalar, but actually has nothing to do with direction. It has to do with the magnitude of the actual thing. For example, if it's a negative charge, it will give negative potential, and it can give negative potential energy. If it's a positive charge, it'll give positive potential. So this is where you will keep, or I would like to keep my positives and negatives, is with potential and energy, and then I just leave my arrows for when I do my vector quantities. Okay, so let's do a little practice with this type of stuff, with the energies and the potential, and sort of see how this actually works. Okay, so let's take something really simple. Here we'll take here's a positive charge, and let's say this positive charge is 0.165 nanocoulombs, and let's say we've got an electron over here, and there's our electron right there. Actually, let's get rid of the electron for now. We'll get rid of the electron for now. Let's just do a little point in space. There's a little point in space, and let's say this is 5 millimeters away. Okay, so I can't find the potential energy there because there's nothing there. So I'm going to just start with finding what is the electric potential there. Okay, well, electric potential, that's just the K, Q over R, and that's it. Well, I've got the K, I've got the Q, I've got the radius, so I'm just going to punch this out and get my electric potential. And should get around 297 volts. So there's my electric potential at that location. Okay, now let's actually put a charge there. Okay, so let's put a proton in there. All right, now if I have a proton in there, this proton can then use that electric potential and have potential energy. So what would the potential energy of the proton be? Well, there's two ways you could do it. You could actually do, KQQ over R, and you could calculate it that way. Or since I have the voltage ready, I can just do QV. So if I multiply the proton charge by that 297, I will have the potential energy of that proton, which gives me about 4.75 times 10 to the negative 17 joules. So that's the potential energy of that proton. Okay. Now, what if instead we switch that proton out and we switch that to an electron? So what would the potential energy of the electron be? Well, it'd be the exact same calculation. There's no difference. The charges are the same. All of that is the same. The only difference is when I would calculate it, I would end up getting negative 4.75 times 10 to the negative 17 joules. I'll clean up that one a little bit. There you go. And that would be the only difference. And yes, that negative is actually really important. Okay, so this is where you want to keep your positives and negatives and that type of stuff. Okay, but that would be the sort of the difference between the two. All right, so let's take the proton. Let's use the proton a little bit, and we'll sort of sideline the electron idea there a little bit. Let's take that proton. We're going to put that proton here. So now this is going to be a proton, and obviously this positive charge would push that proton away. It's going to repel that proton. And let's say it's gone 3 millimeters. Let's find out how fast it's going after the 3 millimeters. Okay, now this is just like what you guys have done previously. Okay, it has potential energy at this location. It's got potential energy at its new location. And just find that change in potential energy. So this would be our EP1. This is how much potential energy the electron or the proton started with. Okay, so my EP1, we already have that. That's 4.75 times 10 to the negative 17 joules. And then the proton moves farther away. So I'm going to find my new potential energy, which is going to be Q over radius 2. And the radius 2 would be the 8 millimeters, because that's how far away it is when it's all done. So let's find out the new potential energy. Let's see, that gives us, and it should be less, yeah, 2.97 times 10 to the negative 17 joules. So remember, as you get further away, just like with gravity, your potential energy becomes less and less and less. Now again, also just like gravity, it's not about how much energy you have, it's all about the change in energy. So if I do that, I can subtract the two. I've got the 2.97 and I will subtract the 4.75, and my change in energy is 1.78 times 10 to the negative 17 joules. So that is my change in energy, and now I can do whatever I want with this change in energy. So for example, this would also be equal to the change in kinetic energy, just like when you guys did with gravity. So this would be equal to 1/2 mv squared, and I can find out how fast the proton is going. Just make sure you use the mass of a proton in there, not an electron, and then square root the v squared, and you've got the speed of the proton. And if we do this, we should get around 1.46 times 10 to the 5 meters per second. Just make sure when you do that change in energy, don't use the negative, because that'll mess up when you want to square root and stuff like that. So you just drop the negative, and it's all good. Okay, now of course the other thing that we can do with this, the exact same way we did it with gravity, is we can take this, and this is also the work that was done. And with that idea, we could find out, just like you did with gravity, we can do work equals force divided, or force is equal to work divided by distance to calculate the average force that was used. Of course, the work that was done is that same change in energy, and the distance would be the 3 millimeters, because that's how far it actually went. So we can take that 1.78 to the power of negative 17, that's how much energy, the change in energy, the work was done, and divided by the distance it actually traveled, which is the 0.003 meters, and we get a force of about 5.9 times 10 to the negative 15 newtons was used to move it. So exactly the same thing you guys did with gravity. Okay, so once again, you could, for force questions like this, I mean, you could try and do the kqq over r squared, the kq in atom. It does not work. It's all about using energies and the change in energy. That's what you want to use when the radius is changing like this. And you could take this question, change the q's to masses, change the constants, and it is identical to what you guys did with your gravitational stuff.